Let's pick up where we left off on the last video and better define what an eigenvalue problem is. So let's first tag everything that we have in an operator equation to show where the eigenfunctions and the eigenvalues are. So in an eigenvalue problem, we have an operator, we have an eigenfunction appearing on the left and the right side, and we have an eigenvalue which appears on the right side as a constant out in front of the eigenfunction. Eigenvalue problems often occur in quantum mechanics as a set of eigenvalue problems. So we have still a single operator, but we have a set of eigenfunctions which are designated here by psi sub n, and a corresponding set of eigenvalues represented here by the constant set a sub n. So let's look at an example of an eigenvalue problem where we have a set of eigenfunctions sine of n pi x, and we're asking the question, find the eigenvalues of the operator a hat, where the operator a hat is defined as the negative of the second derivative of the function. Before we get started on this, let's make a note about taking derivatives of the sine of a function. So when we're taking the derivative of the sine of a function, we're using the chain rule. The sine here is the outer function, and the ax here is the inner function. And recall that the chain rule says when we take a derivative of a composite outer of inner, we get the outer prime of the inner multiplied by the inner prime. So our derivative is going to be the derivative of the outer function, which is cosine of ax, and then multiplied by the derivative of the inner, the derivative of ax, which is a. And so let's put some tagging marks on there. So here we have O prime of I, and here we have I prime. So we are applying the operator a to the function sine n pi x. Rewriting that, we get that means applying the operator minus the second derivative to the function sine n pi x. And this means, second derivative means we're going to take the first derivative of sine n pi x, and then after we do that, we're going to take the derivative again and multiply it by a negative sign. So continuing, we're going to perform this action, which gives us the outer prime of the inner times the inner prime, and then we need to take the derivative of this expression again and multiply it by a negative sign. We have moved the constant n pi out front with a negative sign and indicated that we have to take the derivative of cosine n pi x. And so we have done that here. Here is the minus n pi that was already out in front. When we take the derivative of cosine n pi x, the derivative of cosine is minus sine, so that's the outer prime. We leave the n pi x in there, and then we multiply by the derivative of n pi x, which is I prime. And then if we put that together in more succinct form, we have minus, so it's positive. We have n pi and n pi, so that's n squared pi squared, and then we have sine n pi x. Or we have that a of sine n pi x equals n squared pi squared n squared pi squared sine n pi x. So here is the eigenfunction on both sides, and the n squared pi squared is the eigenvalue. And here we have that summarized on the next blackboard. We have identified the eigenfunction on both sides and the eigenvalue, and we've written the set of eigenvalues here separately. So let's look at a second example of an eigenvalue problem where we're trying to show that the eigenfunction e to the I kx is an eigenfunction of the operator p sub x, which is defined as minus I h. I is the constant square root of -1, h is Planck's constant, and then we're taking the first derivative with respect to x. So p sub x is defined this way, and p sub x is actually the position operator. Let's make note of the fact that I squared, when we square the square root of -1, we get -1. And let's also make note that when we take the derivative of e to the ax, this is a chain rule problem. We get the derivative of the outer function evaluated at the inner function, and then we get the derivative of the inner function ax, our I prime. So we're applying the operator p sub x to the function e to the I kx, which means we're taking the derivative of e to the I kx and multiplying that by minus I h. So we have taken the derivative, which gives us the derivative of the outer function, the exponential function evaluated at the inner function, and we're multiplying by the derivative of the inner function, and then we're going to combine all the constants together to get this, and then take note of the fact that I squared is -1, so minus I squared is just 1, so we have this. So we have hk e to the ik, and that is the same as hk times the function that we started with. So summarizing, the operator p sub x applied to the function e to the I kx gives us hk times e to the I k, e to the I kx, and that means that hk is the eigenvalue, and of course e to the I kx was our eigenfunction. Now we're going to talk about the most important operators in quantum mechanics, operators that are Hermitian. And Hermitian operators first satisfy the property that the eigenvalues that we get A must be real numbers. In fact, all the operators we work with in quantum mechanics have the requirement that the eigenvalues must be observable quantities, and so that means they must be real number eigenvalues. And the second requirement for a Hermitian operator is that it satisfies this integral equation, showing that an operator A satisfies this integral equation is fairly complicated. It's going to take a couple or three blackboards to show that in our next example, but let's first identify the aspects on both sides of this equation. Notice that there is an asterisk on top of the function psi here, and on the other side there is not an asterisk on the function psi, whereas on this side of the equation there's an asterisk applied to the operator, or applied to a times the function psi, or a applied to the function psi, whereas there is not an asterisk here. So first let's identify what that asterisk means. The asterisk stands for the complex conjugate, and a complex conjugate means that if you start with a complex number and take its conjugate, you turn it from a plus bi to a minus bi. Let's also make note of the fact that we are integrating between minus infinity and infinity, and for all of the functions that we work with in quantum mechanics, we have that the limit as x goes to either plus or minus infinity for any function we work with, either f or f asterisk, that limit goes to 0. So in this example, we want to show that the kinetic energy operator, we're going to call T hat, we want to show that it is Hermitian, and T hat is going to be defined as minus h squared, where h is Planck's constant, divided by 2m, where m is mass, times the second derivative operator d2 dx2. So what we're going to need to do is verify that the left side, this integral on the left side, equals this integral on the right side. Our approach is going to be to take the integral on the left side and turn it into the integral on the right side. We're just going to go in that one direction, but the process that we're going to do is reversible, so we don't have to go back the other way. So here we have the integral on the left side, and we have put in place of the operator T hat how the operator T hat is defined, minus h squared over 2m times the second derivative operator. And what we are going to need to do to turn this left side into the right side is apply the integration by parts technique twice. So recall that the integration by parts technique has us in our integral identify a u and a dv. So we're going to designate as our u f asterisk, the conjugate of the function f, and we're going to identify as our dv the second derivative of f with respect to x. So after we've identified u and dv, the parts technique says calculate du, the derivative of u, so that's just going to be the derivative of f asterisk with respect to x. For v, I'm going to ask for your help. V is the antiderivative of dv. If dv is the second derivative of f and v is the antiderivative, then instead of taking the second derivative of f, we are going to be taking its what? Right? Answer, its first derivative. Okay, so we've got all of the elements that we need, and the parts formula says we should get u v minus the integral of v du. So let's set that up. So we have everything set up in the uv minus integral v du form. Let's identify everything, those, to make sure it's clear where it is. So this constant that was in our integral that we're resolving with the parts technique, that constant minus h squared over 2m is in the uv part and the minus integral of v du part. The f asterisk is u, the df dx is v. On the other side we want to have v du, so here is the v and here is the du. Now recall that we said on the previous slide that when either f or f asterisk are going to infinity or minus infinity, it becomes 0. So this element of this left-hand side, f asterisk, is going to 0. So since everything is multiplied together, this whole expression goes to 0, and we are left with this part here. And so let's take this integral that we are going to have to resolve by applying the parts technique a second time, and we'll pick that up on the next blackboard. So looking back to the original part here, what we're actually trying to do is get the f asterisk off of this and move it over to here. So when we look at this part of it here, we want to make our u df asterisk dx because we want to turn that into a second derivative, and we want to make dv equal to df dx because we want to remove the derivative on f. So calculating du would be the second derivative of f asterisk with respect to x, and v, the antiderivative of the derivative, gives us back to our function f. So applying into the parts formula, uv minus the integral of v du, we have the constant out front, h squared over 2m. The u is df asterisk dx. The v is f. This part, the uv part, is from minus infinity to infinity. Because we have the f in there and we're going between minus infinity and infinity, this whole expression goes to 0. And now let's do the minus the integral v du part. So we have minus, put the constant there, h squared over 2m, the integral between minus infinity of infinity and infinity. The v part is f, and the du part is d2f asterisk dx2. Now we are actually done at this part. We just need to write this in a different form to see that we have what we want. So let's bring that constant inside the integral and group it differently. So let's write as minus integral between minus infinity and infinity f, and then we'll put the constant h squared over 2m second derivative with respect to x of f asterisk dx, and we'll put a grouping symbol around this because that is t asterisk. So that is t asterisk applied to the function f asterisk, or I'm sorry, it's t applied to the function f asterisk. And it turns out that t applied to f asterisk is, and it's not easy to show, we're just going to accept that it's true, is the same as t, that is t hat, t hat applied to f, and then taking the asterisk. So another way to say that is applying the operator t to the complex conjugate of f turns out to be the same as applying the operator t to f and then taking the complex conjugate. The easy way to see that that is true is because this is a valid quantum mechanics problem. All of the eigenvalues are real, and so going from f asterisk before and after doesn't really change anything, because if a function isn't complex, its complex conjugate is the same thing, right? A plus bi equals a minus bi when there's no complex part of the function, which is the case here. And so that is the same as the integral between minus infinity and infinity of f minus h squared over 2m d2f dx2 asterisk on the outside dx, and that is the same as what we were trying to get at the start, the integral between minus infinity and infinity of f t hat f asterisk dx. So we got what we wanted to get. I'll just take us back a couple of blackboards to show that this is what we were trying to get, right, with the asterisk on the outside here of the second function under the product. So this is going to conclude our second video on operators, where we've gone through the complex process of showing that an operator is Hermitian by showing that it satisfies this integral property. We applied the parts technique, satisfies this integral property, and we applied the parts technique twice to do that, and we showed that the asterisk that was here goes away, and this t applied to f, which didn't have an asterisk on it, we showed that it does. We can transform it into it having that asterisk on that, and that was this final step here. So our next video on operators will look at a couple of other properties of operators, none as complex as this one that we just did, where we had to apply parts twice. This would be the most complex operator process that we will look at.